Okay, so we were talking about currents, and in particular we covered the necessary background in multilinear algebra and forms. So remember, U was open in our n plus k, or in general, I think we were calling it RP actually for some P, and dnu was the set of n forms, smooth n forms. Omega equals sum omega alpha dx alpha, and this was alpha in INP. Remember, that means that alpha is multi-index J1 up to Jn, where J1 up to Jn is an increasing sequence between 1 and P. And this, as usual, means dx J1, wedge dx Jn. And so now let's start talking about currents. So the set of n currents is just the dual space of this. It's the set of linear functionals on this space. Notice that D is 0 of U. That would be the dual space of D0. And remember, D0 are just the C infinity functions of compact support. And remember that's just, if you've done a course in distribution theory, that's just the Schwartz distributions, which hard to say that they're not important. So this is the set of Schwartz distributions. Or generalized functions, in other words. So let's try and work out what dn for n bigger than or equal to 1 look like. And what are they supposed to generalize? These guys, when n is equal to 0, generalize the notion of function. So what do these guys represent for n bigger than or equal to 1? Well, it's best just to take the prototypical example. It is a really important example that we'll keep referring to. For n bigger than or equal to 1 is the current that you get by start off with an n-dimensional C infinity embedded submanifold of our n plus of our P. And suppose it's contained in our open set U, and suppose it has the property that Hn, the Hausdorff measure of M intersect K, is finite for every compact K contained in U. Then there is one of these currents. You define a linear functional. I'm going to define now a linear functional related to this submanifold. Namely, you define, I forgot to say oriented. So I've got to remind you how that works. So let me defer this for just a second. So recall that you can integrate forms over an oriented manifold. So what's an orientation? For M. Well, that just means that it's an n vector, so it means xi is equal to plus or minus tor 1 wedge up to tor n at each point x in M, and tor 1 up to tor n is an orthonormal basis for the tangent space. Orthonormal basis. tangent space at each point x. And this, in the classical setting, which this is, when M is a C infinity submanifold, you normally require that this vary continuously. So psi continuous function of x. Now notice that xi is an n form, so psi at x is in lambda n of Rp. In fact, it's in lambda x of this subspace, the lambda n of this subspace. So that's what we mean by an orientation. Now remember that you can integrate, for such an oriented manifold, you can integrate an n form with compact support. So here omega is any n form with compact support in U. Namely, integral over m of omega means, well, you may have seen a treatment of this in differential geometry. It always totally bemused me. I could never understand the definition, I guess because I had it when I was an undergraduate. And they always explained integral of forms by using local coordinates and an orienting form. And it never became quite clear to me until quite a bit later what this really means. What it really means is that you integrate over m with respect to Hausdorff measure. Of course, that's just the ordinary volume measure. And you take the dual pairing of omega with the orienting vector. That's all it means. So that's what it means to integrate a form over the manifold. Of course, you can give a treatment of this in terms of local coordinates and so on, but from our point of view, this is a really nice, very explicit way to describe what it means to integrate a form over the manifold. And notice that this really is a linear functional, and it's certainly continuous. So observe, so this is clearly continuous in this space. Remember, this space is topologized by saying that omega j tends to omega in dn of U means that, well, remember it means two things. One, that all the supports are contained in a fixed compact set independent of j. This is for every j, there's some better to say it this way. First requirement is that the union j equals 1 to infinity is contained in a fixed compact set. And the second requirement is that all the derivatives of omega j and all its derivatives converge uniformly to the corresponding derivatives of omega. So that's what we mean by the topology here. And trivially, then, this is certainly continuous. A linear functional. Notice it's real valued, so it's a linear functional on dn of U. So it's one of these currents. So we give it a name because it turns out to be sort of the important prototypical example that motivates all the main definitions. So we write it this way. So this means it's the current, so it's in dn U, and it's defined to be simply the integral of the form over omega, or if you want to be explicit about it, integral omega dual pairing dhn. So that's sort of a prototypical example, and it's going to, as I say, it's going to motivate all our definitions. First thing is, so now let's make some general definitions about currents. Okay, so the currents are just simply the n currents are simply the dual space. So take T in dnu. Now you remember that if we come again back to this example, the Stokes theorem, if M is a manifold with boundary, smooth boundary, called as usual boundary of M, and Stokes theorem tells you that the integral of d omega over m is the same as the integral over the boundary of omega, and this is for any n minus 1 form. Stokes' theorem says that. So that motivates us to define the notion of boundary for a general current T. So the definition is, notice this side would be, in terms of this side would be, in terms of this notation, this side would be m hitting d omega. Whereas using the same notation for the boundary manifold, this side would be the current corresponding to the boundary manifold. Assuming, of course, this Stokes' theorem always assumes that the boundary manifold receives a natural orientation induced from M, because it's the boundary. So there's a unique conormal, and you can, as long as everything's smooth with a smooth boundary, you can of course give a natural orientation to the boundary. And that's what's assumed here in the Stokes' theorem. So this is so that motivates the definition of boundary generally. We say that boundary of T is the n minus 1 current that you get by taking T of d omega. And that's for any omega in d n minus 1 u, and any n minus 1 form with compact support. So that's nice. It's very nice, simple definition, and it's certainly motivated by this Stokes' theorem. And notice, so let's get a couple of properties. Notice that boundary of boundary is by definition then d squared omega, but of course that's 0 because d squared is equal to 0. One of the properties we talked about last time. So it does behave, I mean, that's what a boundary operator is supposed to do, right? It's a boundary of the boundary is supposed to be 0, and indeed it is in this case. So that's our first definition. And also, again, motivated by this example, you can also define the notion of mass, the mass of T. Well, that would be just the total volume, if you like, or total area. In this case, the mass should work out just to be the n-dimensional Hausdorff measure of this guy. So, in general, the definition, so this is our first definition. Second definition is that the mass of T is defined to be sup over omega over n forms with compact support of T omega, where length of omega is less than or equal to 1. Remember, omega is sigma omega alpha dx alpha, and remember this was an orthonormal basis for the forms, so length of omega rather, is just the alpha in IMP. So length of alpha by definition is just the usual Euclidean, just the inner product induced from the inner product in RP. So it's just the treating these as an orthonormal basis. So it's, in other words, the square root of the sum of squares. Squared. So this is this certainly is a standard way. I mean, it's what you'd call the norm of T if we were really in a Banach space. Here exactly would be the norm of T. So like that. So that's good. And there's a corresponding, more generally, if you take an open set, omega, which is compactly contained in U, that means W bar closure is compact and contained in U. Then you can define M, you can define a variation of this when you restrict everything to W. So we would call that the mass in W of T, and that's exactly the same except that, same as this, except that everything should have support contained in W. So sup over omega in D and U. Same thing, T omega, but now length less than or equal to 1 at each point, and support of omega contained in W. Remember, support of this thing is the union of the supports of these functions, right? So saying the support is contained in K means that each of these omega alphas vanishes identically outside that set, compact set K. So that's our second definition. That. And yeah, what else do I need to tell you? So let's just investigate a little bit what this implies. This is the class of currents that, where, notice that these could be plus infinity, of course, that could happen. That's in general possible. In general. So, so one would hope that by hypothesizing that this is finite for each W properly contained in U, we would get some better properties for T. It would be an interesting class of currents to look at. In fact, by the way, notice that we should always go back to our basic example here to check that our definition makes sense. So what is our definition of mass say for this example? Mass of this guy is by definition sup of this stuff, 1 omega less than or 1 omega in D and U, integral over M omega psi Phn. And remember, xi is the orientation, so mod xi is equal to 1 everywhere. Every x in M. So we just have to take the sup over length psi less than or equal to 1. Well, this is the dual pairing. It's like taking a dot product. If you take the dual element to omega, that would be the orienting form. It's just the dot product of omega with a unit vector in the space of n forms. So trivially, the sup of this over omega less than or equal to 1 would be 1 at each point. So this would be exactly just the n-dimensional Hausdorff measure of M. So indeed, that's what we wanted it to be. That seems like the right definition then. So this does seem like the correct definition of mass, because it does work out correctly in this prototypical example. Okay, that's good. Now, let's investigate a little bit what the finiteness of this means. So suppose T is a current, and current, T and U, and MWT is finite for every W properly contained in U. Remember, this double inclusion means that W is compact subset of U, and W is open. Yeah.
Is the mass always non-negative?
Yes, of course, because the mass is always non-negative because you can. This sup includes the case when omega is equal to 0, so it's always bigger than or equal to 0, trivially, right? Okay, so it might be 0 if T, for instance, if T is the 0 current, then indeed it is 0, but it's always non-negative. Yeah, notice this definition is the same as the answer you get by putting an absolute value there, because you can always replace omega by minus omega, so it makes no difference. Okay, so suppose that we've got one of these T's with this. And let's see what that tells us. Well, in this case, first thing is that you can extend T to be well defined on the space of all continuous forms. T is defined on the space of smooth forms with compact support. The claim is there exists a T bar which extends T to the space of all, let's call it CNU into R, with T bar restricted to DNU, giving you back the original T. And this is the space of continuous forms with compact support. So continuous form, some omega alpha dx alpha, where each omega alpha is C0 with compact support. I claim that you can extend T in this way. Let's check that. Well, take a sequence omega J converging to omega in C. So omega is in Cn now. It's just a continuous form. So omega is some omega alpha dx alpha. And this is in CNU. So in other words, each omega alpha is just continuous with compact support. And suppose that you've got a sequence omega J in Dn. Converging to omega, which of course you can always do. In fact, we'll talk a bit more about smoothing later, so there's no problem about that. You can always cook up smooth approximations to a continuous function, of course. So we can certainly find sequences like that, which converge, and this is in the C0 in this space. So here, in the sense, this means convergence in the sense that Tsui over x in k of omega j at x minus omega at x tends to 0 as j tends to infinity for every compact k. So take such a sequence, and as I said, of course, you can do that. Then, in fact, this has already got compact support, so we can actually, in fact, this is unnecessary. We can just take sup. So support, all of the supports of omega are contained in a fixed compact set K. Compact contained in U, and omega j tends to omega uniformly in U. So that's what we mean by convergence in this space. Notice that means Cn is a Banach space. Well, that's not quite true, because I'll come back to that point actually. If you fix the supports, Cn is a Banach space, but let me get this point sorted out first. So I claimed that you could extend T, in this case, when the mass in W is finite, you could extend T to give you a T bar on this space of continuous forms, and that's clear, isn't it? Because notice that T of omega j minus T of omega L. Now that makes sense because this sequence is in D and U, right? So that makes perfectly good sense. So we know that, but T is linear, so that means this is the same as T of omega j minus omega L. And then we just use the definition of mass in W. So as long as the supports of omega j is contained in W, or W bar, then we get this soup of T is less than, well, notice, I don't think I said this, but it's clear if you look at MW T, absolute T omega, if you make this definition, notice it's clear that absolute T omega is less than or equal to soup of the length of omega over U times the mass over W times the mass T times the mass of T, mass in W of T, and that's for every W in D and U with support omega contained in W. Because, yeah, well, T omega by definition, if omega, it's just linearity, right? Omega can be written as soup of omega times omega divided by soup of omega, but omega divided by soup of omega has length less than or equal to 1, you see? So the definition of mass applies to that, so you just get this factor soup omega coming out. So that's general now, without any restriction on the length of omega. This is always true. So we have that, so we can use that here. So this is less than or equal to MW T times mod omega J minus omega L soup over W, as long as all these supports are contained in W. And that's a correct inequality. Okay, but this side tends to 0, of course, because we're assuming that these are converging in the soup norm. This is the relevant norm, so this tends to 0 as JL tends to infinity. So that means this is a Cauchy sequence of real numbers. It's Cauchy in R, and that means it converges. So we simply define T bar omega to be equal to the limit of this Cauchy sequence. J tends to infinity. So that's how to extend. Now you might object, well, one objection that possibly might arise here is, well, what if we take a different sequence converging to omega? How do we know this is the same? Well, of course it's the same, because you can interlace a new sequence with this old sequence. The same argument will still work. You're still converging to W, so it's still Cauchy. So you get the same limit. So you can certainly extend. So this claim is correct. You can certainly extend in this space. So that T bar restricted to the smooth forms is the original T. Okay, and that's good. And then we can just fix the supports. Fix W and look at DN. Look at CNW. Well, on this space T bar, so fixed W compactly contained in U, on that space T bar is a bounded linear functional. I mean, it's a bounded linear functional, so it's norm T bar equals soup over omega in CNW. T bar omega is, in fact, again, it's less than or equal to M. It's less than or equal to the mass of the original thing, right, by construction. So we have that property, so it's finite. So that means this is a Banach space. So we can apply the Riesz theorem. So I've got to remind you of the Riesz theorem, C0. So this is the space continuous n-forms with support contained in W. And W is one of these open sets with compact closure contained in U. So CN's a Banach space. So you can apply the Rees representation theorem to this space. So let me remind you what that says. If you're unfamiliar with this, you'll find a discussion of it in the first chapter of the text. So you can see a discussion of it there. So it's the Rees theorem. And it's the Rees representation theorem is a theorem about the continuous functions with compact support on a compact set with values in a Hilbert space. There's a finite dimensional Hilbert space. And K is compact. And the Rees theorem says if you've got a bounded linear functional in the space, that's bounded, just like this T bar is, sup TV mod V less than or equal to 1 at each point. So V here is the length in the Hilbert space, if that's finite. Then there's a nice representation of, you can describe completely what such functionals look like. Then there exists a Borel regular measure mu sub f, which is finite on compact sets. With a finite, we're taking a fixed compact set here, so just finite measure on this compact set K, and a unit vector U is and a Borel measurable. In fact, a mu f measurable. In particular, you can make it Borel measurable. So in particular, it's mu f measurable. So Borel measurable unit function into h. So it's defined U into h with mod mu equals 1, mu almost everywhere, and with and with integration, f given by integration. So f of f for any f in the space, continuous functions with compact support mapping into h. F can always be represented as the dot product. You take the dot product in h. So this is fx dot u of x d mu of f of x. So that's very nice theorem. Tells you exactly what the linear functionals on this kind of space look like. Bounded linear functions on this sort of space are given explicitly by integration of the dot product between f and a fixed unit vector function with respect to this measure, which is finite measure. So we just have to apply that general theorem to this case now. So Rees, this general theorem, implies that T bar omega is equal to the integral over u of the dual pairing. Now notice in our case we could either take the dot product or we could use the dual pairing. Same result either way. For us it's better to take the dual pairing. So instead of the dot product I'm going to take the dual pairing. So this is omega dotted with something that we call T arrow. This is exactly related to this. It's exactly the nu that you get in this case. A d mu t. And here, so T arrow is at x is a covector, so it's in lambda in Rp. And it's got length 1, like this vector nu here, length 1. Mu t almost everywhere. And mu t is a Borel regular measure on u, which is finite. We're applying this Riesz theorem on each one of these w's. So it's mu t w is finite for every w containing u. So that's really nice. It says that, so the upshot is that if you make this assumption that the mass is finite, notice this is the same as t now if omega happens to be smooth, so it really does give us a representation for t. We only use this artifice of taking t bar so that we could apply the Riesz theorem. Once we've done that, we just go back to t. So we just drop the bar, just restrict omega to, so this is now, this is the same as t by definition for omega in d. So fine. So we do indeed get a representation for t in terms of integration, a dual pairing of the form against a unit vector integrated with respect to a certain measure depending on t. So that's actually a nice fact, and notice it's very analogous to this guy. In fact, this is a special case of this general theorem. In this case, T arrow, if we let this be T, for this special example, T arrow is just the orienting vector xi. See? And d mu t is just, mu t is just hn restricted to m. So this is rather nice. It says that even if you, in the very general setting of currents, as long as you make this assumption that the local mass is finite, then you do get this explicit representation in terms of integration against a measure and dual pairing with a unit vector, covector, and covector. This is T arrow, sorry, I said this wrong. We're taking the dual pairing here, so this is an n vector, not an n covector, so it's lambda sub n Rp. Okay, so that's very nice. It means that as long as you're willing to assume that your currents have got this local finiteness of mass, then you get a very explicit representation in terms of integration. And it even extends to the case when omega is just continuous. In that case, this would be T bar, but it makes sense. This side makes sense still. So. Okay, so that's good. So most of the time we will be talking about currents with this property. Not always, but most of the time we will. So that's going to be an important result for us. Okay, so another couple of definitions. Well, once we've got this, then you can, for currents of this type, in other words, for currents satisfying this, you can then restrict, there's an operation called restriction. if A is a Borel set contained in U, and T is one of these currents, finite for every W properly contained in U, then of course you can make sense of this definition. You can define a new current that you get by in the appropriate sense restricting to A, which really is not quite the same as restriction to A, but that's what typically people refer to it as. Then this is simply the integral over A of omega T arrow d mu T. And more generally, if phi is a Borel measurable function, and the integral of mod phi d mu T is finite, then you can talk about restricting T analogous to this. You can talk about restricting T to phi. And namely, that's just the integral over U of the same stuff, but integrating phi now. Mu T. Okay, so yeah, there's a lot of definitions here, I'm sorry, but I will get through them. Yeah, in fact, we're about to get to something much more interesting, so let me see if I can get to that before the break. So that's important, and also generally the support of T. We haven't talked about that yet. The support of T for a general current T in D and U the support of T, well, it's simply defined to be the union of all the open sets. The open such that T omega equals 0 whenever support of omega contained in V. So that's, notice by definition this is an open set because it's a union of open sets. Sorry. Oh, complement. We're talking about the support. Sorry. Thank you. U minus, so this is closure in U, so it's U minus this. So that's the support. It's a closed set by definition, and notice that support of T is exactly the same as the support of this measure in the case when you're in this setting where the mass is locally finite, and you can use this. Notice trivially the support, if you check it out, just using this explicit formula, you'll see that the support of the current is exactly the same as the support of this measure. So support of T is the same as the support of mu T if mu T exists. In other words, if MWT is finite for every W properly contained in U. All right, so after the break I want to talk about it much more interesting. So they're the sort of basic definitions that we're going to need, but let me tell you a rather more interesting result, which we'll talk about after the break. And that is the compactness theorem. Namely, if you take a sequence TQ contained in currents, T and U, and if the mass soup over Q of mass W Q TQ is finite for every W contained in U, then there exists a current T, TQ and D, and these are currents in the dual space. So then there exists a T in DNU such that, and a subsequence. Subsequence TQ prime such that a TQ prime omega converges to T omega for every fixed omega in DNU. So in this weak sense, there is always there is a limiting current with the property that in this weak sense TQ converges to that. So we'll talk about that after the break. Let's take a 10-minute break.
That reminds me, once I was at a conference somewhere in the U.S. that I was in the second or Freddie was. I was fast asleep. And Freddie was unaware. This was true. I think I'm going to be sleeping in this and, I'm supposed to be, Freddie's until you get to something interesting. You're still doing your regular work? I once made the mistake of using this course. I made the mistake of you know, that would be better. So, even though it's not correct, but it would be better. This damn Russian guy, what's his name? And that would be better. You know, guy's written a number of books on I can't remember his name. It's a disaster. Just waving his arms and you sort of glance at it and it looks okay. You really want to look at the detail. It's not really there.
Okay, right. Leave that one there. Okay. All right, so let's continue. So let's see if we can prove this here. By the way, this is not the dramatic compactness theorem that I mentioned a couple of lectures ago. This is the so-called easy compactness theorem that doesn't say much about anything about it's very general because you just take an arbitrary sequence with this property. So this is really just a theorem in functional analysis. It's not like the compactness theorem that I talked about, that I mentioned, that we're going to talk about later, about the real compactness theorem of Federer and Fleming. But let's see if we can, in any case, prove this. So, right, the first step is to use the same idea that we mentioned before. Because we've got this property again, we can again extend to Cn. So, extend TQ to TQ bar, which are continuous functionals on CNU rather than DNU. Same, where the coefficients now, these are just continuous forms with compact support. So we do that, exactly the same as we did here, just extend in exactly the same way. And then we take again a fixed W, and restrict everything to that set W. And then we're, okay, then we have a sequence, so TQ bar restricted to CNW is then again a Banach space, as it was before. Same argument really. This part of the argument is the same as the argument we gave a few minutes ago. So it's Banach space, so we can use functional analysis again. This time we're going to use the so-called Banach-Ala-Oglu compactness theorem. So the Banach-Ala-Oglu compactness theorem implies that indeed there exists a subsequence Q prime, subsequence TQ prime bar with TQ prime. So we do this for each W, apply the Banach-Ala-Oglu for each W. So technically you're going to have to take an increasing sequence that eventually chews up all of U, but it's pretty clear that you can do that. So there you get a subsequence and a T in a T bar in CNU with T Q bar omega converging to T bar omega for every omega in DNU. And as I said, you really do this for a fixed W first and then take an increasing sequence of W's in order to get the statement like this, where you actually get a limit you actually get a functional, limit functional on the whole space, DNU. Okay, so that's Banach-Ala-Oglu, great theorem, of course, but very general. And of course, once we've this is for every W, for every W in CNU initially. But of course, now we restrict. This is just TQ prime, omega if omega is in DNU. Likewise. So that converges to T bar omega. So that's it. You just take T to be this thing, T bar restricted to DNU. Instead of taking the functional on CNU, you restricted. So there's not much to that theorem, but it is nevertheless a very useful theorem. It's sort of the first step of the main compactness theorem that I mentioned, and which we will talk about later. Okay, so that's the easy compactness theorem. And let's see, what else? Oh yes, a couple of other operations that we still need to talk about because we're going to need them in rather important ways later. So next thing I want to talk about is pushing forward currents. Remember, we talked about pulling back forms. Now the currents are the Joule space of the form, so you should push forward currents apparently. So let's talk about that. Okay, so maybe leave our prototypical example there because I want to keep referring to that. Uh-oh. I guess if I had sufficient intelligence, I could work out how to turn that thing off, but I'm afraid I cannot.
It's not up, but
Yeah.
somehow it's just turned on by itself.
So it's not even turned on at the wall, you mean?
Yeah, so
Yeah, okay. Okay. Right, that's okay, we'll persevere. All right, so let's talk about pushing forward. So suppose that F is a map from U to V, and U is open, contained in Rp, and this is a C infinity map, and V is open in Rq. So we've got this. F. And as usual, of course, we're going to require that, see, we want to be able to pull back forms of compact support and still have a form with compact support. So it's important that F be proper, right? So F proper, meaning the preimage. So as we discussed, F to the minus 1 compact in U whenever K is compact in V. So whenever you take a compact set over here and you get the pre-image, that's a compact subset of U. You'll see there's one of the problems for this week. It gives you an alternative, much more intuitive way to look at what this means. Okay, so that's the setup, and suppose now we take a current T, an N current T, E and U, and we want to define what I want to define a current. I want to push that forward to give a current over here. So we start off with a current here, and I want to push it forward to give a current over here. So F sharp T. So I have to say what F sharp T does to a form over here. So omega. So omega is going to be a form over here. So that's going to be in V, in form with compact support in V. And of course the natural thing is simply to define that to be T F sharp of omega. Now that's good, that works, but this is a bit too restrictive for applications. You can relax F being proper. It's sufficient that F intersect the support of F restricted to the support of T be proper. And then we're going to have to modify this. So this is fine, that makes sense as a definition, and I'll work out in a minute how it works for our prototypical example here, make sure it gives what we expect it to give. But this is a bit too restrictive, so let's make the following observation. So note if F restricted to the support of T is proper, that's a weaker condition and it's more useful in practice. Then you can give an alternative definition. Then you make a slightly modified definition. You define F sharp T of omega to be equal to T of zeta times F sharp omega. And here zeta is a C infinity function with compact support in U. This is all happening in U. Remember, we're taking a form omega in D and V, and we're pulling it back. So this is all happening back in U. So this C infinity function with compact support in U, and zeta identically equal to 1, zeta identically equal to 1 in some open set W, which contains the compact set support T, support zeta rather, intersect support T. Notice that's a compact set, of course, no question. And also notice this trivially is okay. This makes sense because it doesn't matter whether F is proper or not. This is certainly got compact support, so at least it makes sense. However, there's a catch, as there always is with these sort of definitions. We have to check that this is independent of which particular zeta we take, right? So we've got to take another zeta and check that we get the same answer if we do this. So let's check that. So check that this makes sense. Well, it certainly makes sense, but in particular that it's independent of zeta. I mean, this side is certainly defined, no question, but check that it's independent of the choice of zeta as long as we stick to these conditions. That zeta should be identically 1 in a neighborhood. Notice this is a compact set, so you can certainly construct such a function which is identically 1 in a neighborhood of that compact set and still has compact support in the big domain U. So you can certainly do that. And in fact, the picture is something like this. Schematic picture is something like this. Here's U, and here's the compact set. This is compact, this is support zeta intersect, sorry. This is support, I said this wrong. Sorry. I'm supposed to be talking about this guy. So support F sharp omega intersect support T. Now that is a compact set by this property. So that's certainly compact. So this is support F sharp omega intersect support T. So that's the compact set, and then you take a zeta which is identically 1, so this is, I'm drawing the graph of zeta now. Then take zeta to be identically equal to 1 and then to go down to 0 so that it's still got compact support in U. So this is the graph of zeta. So that's, you can certainly do that, no question. So you do that, but now we've got to show that it's independent of the choice of zeta. So take another such zeta. So take another zeta tilde satisfying the same conditions, identically 1 in the neighborhood of the support. And then observe that T zeta F sharp omega minus T zeta tilde F sharp omega. By linearity, that's just T of zeta minus zeta tilde of F sharp omega. And this guy is identically 0 in a neighborhood, in fact in the same neighborhood, in a neighborhood of support F sharp omega intersect support T. And that means, of course, this is 0. The right side is then 0. So indeed, this is definitely independent of the choice of zeta. So that's good. So this not only makes sense, but it's independent of the choice of zeta. So you can make that as, we can make that as our definition of pushing forward the current. And there are other things to check here. The other thing to check is that this is, of course, still a continuous linear functional. It's still a current, but of course that's very easy to check because the topology in DNV is rather in DNU is so strong, and DNV for that matter is so strong that it's trivial that that's certainly a continuous linear functional. So that makes sense as our definition of proper. Now let's check that it works out as we expect it to work out if we go to our prototypical example here, this one. So let's so here we'll suppose that M is contained in U, and same hypotheses, F U into V, C infinity, and then the support, in this case, the support of the current, of course, in this case, is just the closure in M. So M bar intersect U. F restricted to M bar is proper. Okay, let's see if we can work it out. So what would our definition say for this example? F sharp of M hitting a form omega, by definition, would be we put in this function zeta and we pull back omega. So it's the integral over M of zeta times F pullback of omega psi. Psi is, remember, the continuous orienting vector. So remember, psi is nothing, at each point it's either plus or minus tau 1 wedge up to tau n, where tau 1 up to tau n is an orthonormal basis for the tangent space. Dxn. So that's what we get. Now, notice we can play a little game here with the duality. Remember, part of the so remember how this works. By definition, this means, well, the first thing is we can drop zeta. Because zeta is identically 1 in the neighborhood of M bar intersect the support of this. So it's always 1 in the domain of integration. So that we can drop, get rid of zeta immediately. The other thing is, remember what the definition of this is. It's dfx sharp of omega at fx. Paired with psi at x. Dhn. We're integrating always with respect to Hausdorff measure for this example. And that, by definition, remember there's duality here, so we can, instead of pulling back this and pairing it with that, we can push forward that and pair it with omega. So this is omega at fx times dfx sharp psi dhn. So now we've got to work that out. So let's do that. And we've done this sort of thing a few times, so it shouldn't be that bad. So psi is plus or minus tau 1 up to tau n. So dfx f x sharp xi is dfx sharp tau 1 wedge up to tau n, or plus or minus that rather. And that's equal to, well, remember, one of the basic properties of pushing forward n vectors is that you can push forward the individual vectors and wedge those together. So this is plus or minus dfx sharp tau 1 wedge up to dfx sharp tau n. So, and that's, well, this is just the induced linear map heating tau 1, that's just the directional derivative in the direction tau 1. So tau 1 f of x, wedge, etc., up to d tau n f of x. So plus or minus. And now we can work that out too. That's the same as I can, now we've got to think about this a little bit. So F is a mapping from M, here's the picture. So U is the big open set containing M. And F, so this is U. F is going into V. And now for I don't want to get into a big mess here computationally, so I'm going to actually assume, let's just look at the basic case here. When F is 1 to 1, you'll see, actually I'll mention it after what happens if you drop that. And let's also assume that F is non-degenerate, rank n at each point. So that's the sort of basic case, rank n for every x. Each x in M, rank n at each x in M. So that means this. So then we know that the image, so this is a 1-to-1 map, and the image, Fm, is then a submanifold. C infinity submanifold of V. In fact, you can get the local coordinate representations for Fm by using the local coordinate representations for M. So the local coordinate representations, you simply use F composite with C. So you take C, giving you the local representation of M, compose it with F, and that gives you a local representation for Fm. So you can check that that satisfies all the conditions of our definition of submanifold. So certainly it's a submanifold. So it's a submanifold, and F is taking taking M into this submanifold. So what can we say about this d tau 1? Well, it's the directional derivative of a function mapping into F. So clearly that's a tangent vector at the limit point. So notice that d tau 1, just consider curves passing through the various points. You'll see by definition of tangent space that d tau 1 up to d tau n f of x are actually all in the tangent space at the image point of this submanifold M tilde, where M tilde is equal to Fm. So M tilde equals Fm. So they're tangent vectors. And take an orthonormal basis for the tangent space at that image point. So e to 0 will be orthonormal for the tangent space at the image point, f of x. So do that, and you see then we can work, this will then be a linear combination of these e to j's with various coefficients. In fact, we can write it like this. D tau 1 Fj is the sum from J1 equals 1 up to n of eta J1 dotted with the tor 1 f of x. And the same thing with the other tors. So you see how that works out is that you get a sum over J1 to Jn, 1 to n, of d tor 1 fx dotted with eta J1 times d tor 2 fx dotted with eta J2, and so on, up to d tor n fx dotted with eta Jn. And what we have left after we pulled out those linear factors is the wedge product of eta J1 wedge to eta Jn. And right, we recognize that there's only, this is just, well, first of all, we need only worry about summing over distinct J1 up to Jn, because we know that these wedge products are always 0 if there's any repetition there, right? So we can certainly take these to be distinct. So they're distinct, and then of course we can, then this is just a permutation of J of 1 up to n. So if we put the sign of the permutation out the front, so we're actually summing over permutations. Permutations sigma of 1 up to n, and we get the sign of sigma, and then this product e tor 1 fx dotted with sigma j, eta j sigma 1, etc., d tor n fx dotted with sigma j, eta j sigma n, and then what's left is just eta 1 wedge up to eta n, like that. So write it that way. And notice this is just a determinant. This is plus or minus the determinant of d tor I fj. T tor I x dotted with eta j. N by n matrix. And we did this once before. We reckon you remember what this actually is in terms of our previous notation. This is exactly, if you put an absolute value around it, is exactly what we call Jm, the Jacobian map, the Jacobian function. So this is plus or minus Jmf at x. It's the thing that appears in the area formula. So we agree, of course, so we always agree, of course, to choose, so let's call this guy eta. Notice this k vector, it's a k vector, rather an n vector, on the tangent space. It's an n vector in RQ. This is all happening over here in RQ now. This is originally started off in RP, push forward to RQ at the image point, f of x here. We've got these are all in the, this is the orientation, these are tangent vectors, so orthonormal for the tangent space, so eta 1, eta n orthonormal for the tangent space, t f of x, m tilde, or m tilde is the image manifold, fm. So, good, so this is Jmf times eta, where eta is either plus or minus this, and if we agree to choose the plus or minus appropriately, we can get this. So where eta equals plus or minus. You've got to choose the sign appropriately to get rid of the minus sign here. This is then called the induced orientation. induced orientation is the orientation that you choose to make sure you get a plus sign here at each point. Okay, so that's that. Now let's see, where does that leave us? Well, let's come back to here. This then we've shown is the same as integral over m of the Jacobian f omega at the image point f of x times the orientation eta at the image point f of x dhn. And this is, yeah, so it's that. Now, but we recognize, see, this is where we can apply the area formula. This is a function given, function of x given at the image point f of x, which is exactly right to apply the area formula. So because f is 1 to 1, according to the area formula, this is exactly the same as the integral over the image, fm, of omega paired with the orienting n vector, the induced orientation, dhn. So it was a bit of a struggle, but that is exactly what we wanted to happen. So indeed, it appears that our definition of pushing forward is the right one, because it gives the correct result when you go to this prototypical example, because we've just shown that the push forward of our prototypical example just gives the image manifold with the induced orientation. So that seems to be the right definition. So indeed, we stick with that definition. That's our definition of pushing forward. All right, so now let's see. Yeah, okay, let's check a couple of things about pushing forward now. Properties. Oops. Properties. Let's first of all compute the boundary of the push forward. Okay, well, boundary of the push forward is by definition, remember, just the current, whatever the current is, heading d omega. Here omega is any form by pushing forward, so this is a form in the space v, d and v, image space, that we're mapping into by f. And that is the same as, now by definition, that's exactly equal to t of the pullback of d omega times this function zeta, which we used in the definition of pulling back. And now, remember, one of the properties that we checked about forms is that pulling back and d commute. So this is the same as t zeta d f sharp omega. That's good. And then we can, of course, notice that d of zeta f sharp omega is the same as d zeta wedge f sharp omega plus zeta d f sharp omega, trivially by definition of d, you see that. So this, but this term is 0 because zeta is identically equal to 1 in the neighborhood of support t intersect the support of this. So this term is 0. So this, we can simply write this as t, just use this term instead. So this is d of zeta f sharp omega. And by definition, that's the same as boundary of t. Zeta times f sharp omega. Yeah, I forgot this was so long. Bit of a struggle, yeah. And this is, by definition, exactly the same as pushing forward this guy. Got the correct factor of zeta in the front, and we're pulling back the form. So indeed, the first property then is that d of f sharp T, pushing forward T is the same as pushing forward the boundary. In other words, delta and F sharp commute. So that's the first property, and I think there was something else I wanted to mention there. Okay, it'll come to me, so maybe that's enough for the moment. So, so that's pushing forward. And we'll come back to that. It's one of the important operations that we're going to need in our deeper discussion later. And now we've still got a few properties of currents to talk about. One is the very important constancy theorem. Constancy theorem. And that goes as follows. Take any current. It doesn't need to have locally finite mass, just any current at all. And but assume that its boundary is 0. So no boundary. And, oh yes, yeah. And most importantly, this theorem refers to the case when P is equal to N. So U is an open subset of Rn, and it's the same n as the dimension of the current, right? So this is a very special case. So U is, instead of being in P is now in Rn, same n. So this is the top dimension, in other words. We're taking an n-dimensional current in Rn, and it's got 0 boundary. Well, the claim is that in that case, T is just a constant times the current that you get by integration of forms over the open set U. Notice this is the same notation as we're using here in this prototypical case. It's just that it's the special case of this when M is equal to an open set. It's the top dimensional case. Of M when M is equal to U open and U is contained in Rn instead of being contained in Rp, a higher dimensional space. It's now in Rn, right? So, yeah. Yeah, sorry, you're right. I always forget that, right? Thank you. Yeah. Bob just points out that this is actually false unless you, of course, because you might get a different constant for each connected component of U, so we'd better say that, so U connected. It's like the maximum principle in PDE. If you've got a local minimum for a harmonic function, then it's constant. False, unless the domain is connected. It's constant on each component, right? So, yeah. Okay, so so this is the claim. So let's see if we can prove this. So proof. So right. Now let's think about this. What does a current in this top dimension look like, actually? What do the forms look like, actually, in the top dimension? Well, they're just sort of trivial objects. They're a set of a dx1 up to dxn. See, there's only one possible choice of the covector here. It's dx1 up to dxn, and a is just a C infinity function with compact support on U, real valued C infinity function. So that's what the forms look like. So so that's what we're working with here. So let's take the following. So I'm going to have to use mollification here. So I've got to remind you how that works. Smoothing. So you take a phi in C infinity with compact support in Rn. And you require that phi is everywhere positive, non-negative rather, and it's got compact support, and the integral of phi dx is equal to 1. So it's a function that looks like this. It's a function with compact support, and it's, let's also agree that the support of phi is contained in the open unit ball, centered at the origin. So this is the unit ball. And this is what I've sketched here is the graph of phi. Okay, and then you can rescale that function. Phi sigma x is sigma to the minus n phi x over sigma. Now that has a similar shape to this, but everything's compressed to be living in the ball of radius sigma instead of the ball of radius 1. And it's also multiplied by this large factor, sigma to the minus n. Think of sigma as being small here. That's the important case. Multiplied by this large factor. So this is what the picture looks like. So this would be b sigma. And when sigma is small, that's very small interval. And then it goes way up there. There somewhere. And notice by change of variable, this has still got integral equal to 1. That's why you need to put in the factor sigma to the minus n there. So integral phi sigma is still equal to 1. And you use this to mollify functions. So you take a sub sigma of x simply, well, yeah, so let me set things up now. Okay, so right, I'm going to use mollification, and also we're going to be working with these forms. Now, for the moment, let's take, rather than taking a C infinity function, let's take a function in L1 of Rn with the property that support of A is identically 0 outside some ball. Take any point x0, take a row positive. So take any ball, b row x. Take any ball with, actually it's more convenient to take a ball with twice the radius rho, b to be contained in U. So this is an arbitrary ball contained in U, centered at some point x0, doesn't matter where. And take an L1 function, 0. Then you define the mollified version of A sigma of x. That's just the function that you get by taking the convolution with this mollifying function. Or if you want to write it out, this is this mollified function of x. That's equal to integral phi sigma x minus y ay dy. And notice that is indeed a C infinity function. Since the integral is equal to 1, it's very easy to check that this still, even though A is only L1, this certainly converges to A of x for almost every x, Ln almost every x in Rn. This is as sigma goes down to 0. That's the first thing. Second thing is this is clearly a C infinity function. In fact, you can differentiate as many times as you like by differentiating under the integral sign, because you've got a fixed L1 function here. So you can apply the dominated convergence theorem using difference quotients as many times as you like, and just differentiate under the integral sign as many times as you like. So A sigma is in C infinity now, rather than just being L1, and it's got compact support. This is all true as long as sigma is less than rho. We want to make sure that the support of this doesn't, as long as we want to make sure the support of this remains inside U, but there's no problem if sigma is less than rho, because the ball of radius 2 rho is contained in X. So everything makes sense as long as we keep sigma small enough, sigma less than rho, we can do that. So this is C infinity with compact support this is given in U to begin with. See, what did I take? So I was taking A and L1 of Rn. Okay, so makes sense. C infinity on all of Rn. Okay, so we do that. And now observe that we could define a current T sigma. So let's go back to this current here. It's got boundary 0. So T omega is equal to, well, let's see, what is T omega? It's equal to the integral over u. Let's see, no, we don't know that. Well, T's an abstract current, so actually I can't say much about that at the moment, but let's see what we can say. Well, suppose that we've got a sequence AJ converging to A in L1. So remember, A is an L1 function here, arbitrary, identically 0 outside. And suppose that all the AJ are all 0 outside the ball of radius rho. P rho x0. Well, notice that then AJ sigma, that's the smallified function, that clearly converges to A sigma for each fixed sigma. That converges in the space C infinity with compact support in U. Because the supports are all compact, we're just assuming that. They're all 0 outside. And because of this, AJ is converging to A and L1, but so you can take the derivatives, Tx beta, that just gives you a derivative inside the integral here, Tx beta, but it doesn't affect A. So clearly this side, if you replace A by AJ, that clearly converges, as long as AJ is converging to A, that clearly converges back to this for any number of derivatives. So that's exactly the definition of convergence in this space. Remember, this is D0 and D0. So in other words, AJ sigma dx1 wedge up to dxn converges to A sigma dx1 up to dxn. That's in dn. Sort of a triviality because we've smoothed everything out. So that's convergence in dn. But then the relevant T's converge. See, that's what T by definition is a current, means it's continuous in this kind with respect to this convergence in dnu. So let's see what that'll give us. So T, let's call this, so T AJ sigma dx1 wedge up to dxn converges to TA dx1 wedge dxn. So that's good. We get to the relevant, it's true whatever T is, you get that, and this is A sigma. And that means that this is a continuous linear functional. Keeping in mind that this was all true if you merely had AJ converging to A in L1, right? So this is a continuous linear functional on L1 of B rho, x0, the open ball, radius rho. So we've got a continuous linear function on the ball of radius 1. But then the Riesz theorem holds, not the Riesz theorem that I was referring to before, but the Riesz theorem for L1. The Riesz representation theorem for L1, for L1, P rho x0, implies that this functional dA sigma dx1 wedge up to dxn must be equal to A integrated against a function, theta sigma. That's what the Riesz theorem says, called Mustn't forget that whatever function we get from the Riesz theorem will depend on sigma, because we've got a sigma here, right? But the Riesz theorem says there's a non-negative function that you get there, and that this is integration with respect to Ln. So, not necessarily, sorry, that's not right. This is just an L1 function. It may be negative, actually. So theta sigma. And bounded, theta sigma bounded. That's the Riesz theorem for L1. So that's good. We've now got T, this tells us what T applied to this thing sigma is. But now, remember, we've also got the boundary if T is 0. So we're out of time now, but I want to show, so we'll pick it up here from this point next time. This is the main step in the proof, showing that you can write the, at least as far as mollified forms are concerned, you can write the T as an integral of this type, and you can do that for every A in L1 of B rho. But we haven't noticed, we haven't yet used the fact that boundary of T is equal to 0. And I want to show you that that trivially implies that this guy has to be constant. In fact, yeah, well, I've got to stop, but we'll pick up the argument there next time.